Welcome to This Explainer. Today, we're going to unpack an everyday mystery that is quite literally hiding right in plain sight. Have you ever noticed how light seems to just play tricks on us? I mean, most of the time we think of light as traveling in a perfectly straight line, kind of like a tiny bullet flying through space. But it turns out light is constantly interacting with the world around it, bending, pivoting, and just completely shifting its path. Now, our goal today isn't to sit here and memorize complex physics formulas. Nobody wants that. Instead, we're going to build a really wholesome, first principles understanding of the hidden rules of light.
So, picture this. You're sitting at a cafe, you look down at a straw in your glass of water, and it looks completely snapped, right exactly at the surface. Or think about that crazy, shimmering optical illusion you see hovering over a hot road in the middle of summer. Well, these aren't just random glitches in the matrix. They actually all point to one totally fascinating reality. Light is responding to the material it enters. It's not just blindly rolling forward no matter what. The environment it moves through actually dictates its behavior.
All right, let's dive right into this. Section 1. Why does light bend? Uncovering the ultimate anchor truth.
Before we get to that ultimate truth, let's clear up some really common misunderstandings. Light isn't just lazy, and it certainly doesn't get pushed around by a wall. Instead, I want you to absolutely burn this one sentence into your memory. Light bends when it changes medium because its speed changes. Seriously, this is the foundational anchor for our entire explainer today. We're going to build our whole mental model right on top of this single idea. Light just moves differently in different materials. When it crosses from one environment into another, its speed shifts. And refraction, which, by the way, is really just a fancy scientific word for bending, is simply the shape that speed change takes.
Moving on to Section 2. The hidden rules of refraction. Building the mental model. See, refraction isn't some random magic trick. It follows really deep, predictable rules every single time it crosses a boundary, whether we're talking about water, glass, or plastic. So first things first, we have to stop picturing light as a single tiny dot. Instead, imagine it as a wave front. Think of a massive stadium crowd doing the wave, right? The wave isn't just one person, it's a moving pattern across a broad sheet of people. Well, light travels exactly the same way, as a moving front of energy. And grasping this shape is absolutely vital for understanding why it turns in the first place. To actually see this turning mechanism in action, imagine pushing a shopping trolley from smooth floor tiles straight into thick, sticky carpet at a bit of an angle. The front wheel on one side hits that carpet and slows down first, while the other wheel is still rolling fast on the smooth tile. What happens? Boom, the whole trolley aggressively turns. Or, picture a line of people walking arm in arm into shallow mud. The person hitting the mud slows down first, and the whole line pivots. That pivot is exactly what happens to our light wave front. An uneven speed change across the front completely shifts the direction. Okay, before we go any further, we have to make a super crucial distinction, because these two things often happen at the exact same time. Think of a doorway with the big glass panel. Some people might literally bump into the glass and bounce off. That's reflection. But others open the door, step through into a room with a totally different floor, and naturally change their walking pace. That entering and bending, that is refraction. It's the exact same boundary, but two completely different behaviors. So here is our compact map of the hidden rules we just built. Take a look at how beautifully logical this all is. Because light is a wave front, one part of it can slow down first. Because it hits a boundary, that's exactly where the rules of travel suddenly shift. Because the speed changes unevenly, the whole direction pivots. And the bigger the difference between the materials, say jumping from thin air into super dense glass, the stronger the bend is going to be. This simple, elegant physical logic completely replaces the need to blindly memorize a bunch of complex mathematical formulas. Which brings us to Section 3, refraction in the real world. When the rule meets reality. Now that we understand uneven speed causes bending, let's take this mental engine for a test drive and see what happens when we alter the physical shape of a surface. A flat boundary bends everything together in a pretty uniform way. But what happens if the surface is curved? A curved boundary bends rays at different positions by completely different amounts. Think of a massive crowd moving through a doorway that dramatically narrows in the middle. The people are naturally redirected and funneled by the actual shape of the opening. And guess what? This is exactly how a magnifying glass works. Refraction plus a curved shape equals total control over light, letting us gather it all into a single, intense focal point. In reality, though, light rarely hits just one surface and calls it a day. It passes through air, into glass, and then back out into the air again. Every single boundary gives the light another chance to turn. It's kind of like a train running over a series of track switches.
One switch just nudges it slightly, but multiple switches in a row, they send that train to a totally different destination. This cumulative stacking effect is the secret behind those incredibly complex camera lenses and thick blocks of acrylic.
All right, Section 4, Why Your Eyes Get Fooled. The Straight Line Shortcut. This is where the story gets really personal. We've talked a lot about the physics, but we need to talk about human biology for a second. Your visual system is incredibly powerful, no doubt, but it relies on a hardwired shortcut. Your brain stubbornly assumes light always travels in a straight line, and refraction aggressively exploits that shortcut. If you drop a coin in a cup and then pour in some water, the coin looks like it physically lifts and shifts, but we know the coin didn't move. The water bent the light path. But your brain completely refuses to calculate that bend. Instead, it extends those bent rays straight backward, literally hallucinating the coin exactly where a straight line tells it the coin should be. Honestly, the bizarre thing isn't the illusion itself, it's that our straight line shortcut works so flawlessly most of the rest of the time.
So the really crucial takeaway here is that boundaries don't even have to be hard physical lines. Consider that shimmering heat haze we talked about, the one hovering on a sun-baked asphalt road. What you're actually watching is light passing through layers of air at slightly different temperatures. Because temperature actually changes the optical density of the air, the light is constantly changing speed, causing the rays to literally curve and wobble before they ever hit your eye. It's the exact same bending roll we've been talking about, just happening gradually out in the open air instead of instantly at a hard glass window.
Finally, Section 5, A New Way to See. Tracing the cause, not just the effect. So you are no longer just looking passively at optical illusions. You can now look right past the effect and trace the actual cause. You've made a real identity shift today into a true first principles thinker. You know that changing materials change light speed, and that speed change radically reshapes its path. But it does leave us with something pretty fascinating to ponder. Given that every single pane of glass, every tiny drop of water, and even the varying temperatures in the air around us are constantly bending information racing towards your eyes, if your brain is hardwired to assume a perfectly straight path, how much of your world is actually just an optical illusion? Keep observing and keep questioning what you see.